Hello and welcome, guys, to Advent of Code 2022, day 15. So right at the very top of this, I'm going to have to throw up a disclaimer. I've had an absolutely crazy day today outside of Advent of Code. And then on top of that, today's Advent of Code was quite difficult for me. So those two things combined has meant that my solution is not great. And but that's life. Life has to go on outside of Advent of Code, and we get through it. So I'm going to try and get through this really quickly. I'm probably not going to go into as much detail as I normally do, but I solved the puzzle, and I want to keep alive my streak of putting up a video every day. So we're going to just jump straight through into this and go through it. So day 15, beacon exclusion zone. So we've gone through our tunnel, we've gone through our waterfall, we've gone into our caves, and through the caves you basically end up in this whole section of different caves. You happen to have these beacons that you can deploy, and they'll whiz off, or these sensor signals. There's sensors and beacons anyway that they can find each other. That's it. So how does it matter? You've got a set of sensors and you've got a set of beacons. We're told that our input is basically the coordinates of each sensor, and we're told the coordinates of the closest beacon to that sensor. We're also told that within that distance, there is no other beacon that's going to be closer to the sensor from that distance. So this is our puzzle input we're given. We're given all of the sensor locations, and we're given the location of the closest beacon to each sensor. So if we go down and have a look, we can see that we end up basically with a map like this. So we've got all the S's are the sensors, and then B's are the beacons. We're also told that in terms of, say, the closest to each one, we're told that it's calculated on a grid by the Manhattan distance. So the Manhattan distance is, if you're on a grid, it's just the sum of all the x's and the sum of all the y's added together gives you the Manhattan distance between any 2 points on a grid. Okay, so what we're told is, so we're basically given that setup, and we're given all these inputs. But we're told that this isn't actually all of the beacons that exist, and that we need to find, we're basically trying to find a specific beacon, which is like the distress beacon that's currently that we picked up the signal from in the last one. So say here, for example, this is a good display of what that Manhattan distance thing means. So from this sensor, we know that this is our beacon that we picked up. So we were told that for this coordinate, this sensor, that's the beacon that we picked up. And the Manhattan distance is the sum of this distance and the sum of this distance, which I think is 9 here. So within 9 Manhattan distance units of that sensor basically is this sort of diamond shape here. And we are also told that we know that there is no other beacon inside this area. That's based on the Manhattan distance between here and here, and we can see here there is no other beacon. So that's a useful piece of information to know for what they're going to ask us to. So if we go down then to what the problem actually asks us, we're told that pretty much by knowing that Manhattan distance and being able to make that diamond shape for every sensor, we're told that we can essentially know where our distress beacon isn't in the whole space that we have. So what we're asked is for a specific coordinate, a specific y coordinate, which you see listed down along here, how many, for the entire map, how many spaces are we certain there is no beacon? So that's kind of complicated, but let's have a look here. So for this, we're told in our example that we want this to look for the line 10 here. So we can already see that we know, well, there's a beacon there, but we also know that there's there's no beacon in any of these spots because this sensor can see all these areas. So we know that there's not going to be a beacon here. And then if we go down to here where they filled in some more blanks for us, or some more filled spots, we can see that we have this sensor here. So this sensor is going to basically fill in the rest of this area for us. So if we look down here, we've got this sensor. We can see that it's 3 Manhattan distance units up from there. So if we go to any of these points, we know that we've basically filled in that area. And so then for this line that we're looking at, we can count up all of the hashes that we have here, and that will give us the answer to the puzzle. Of course, though, now we're getting to a point of advent of code where the puzzle inputs are getting really big and the numbers are deliberately huge to mean that the naive approach of, just building the grid and populating it is no longer going to work, and just trying to iterate over these things will take forever. So you need to come up with something a little bit clever to try and solve this puzzle. So let's have a look at my part 1 solution. So what I've done is, the first thing I do is I go through all of the inputs and I make a list of all of the sensors. I record the X and Y components, and I also record what the Manhattan distance is from the sensor to the beacon, that'll come in useful later on. So whatever that value is, we're recording that along with our sensor's coordinates. What else are we doing here? Yeah, so then the next thing that we're doing is we're creating a list here so actually I should also say that we have a target Y coordinate here because we're told which line effectively in the Y coordinate we want to look at. So we're told it's 10 for the sample and it's 2 million for the normal input. That will also become important in a minute. So what I do is, for every sensor then, I make this loop where I try and calculate what the difference is between the sensor's Y coordinate and the target Y coordinate. So I get effectively the Manhattan distance between those two. If that's greater than the largest Manhattan distance that sensor can see, then I can skip because I know that sensor can't see that line at all that I'm interested in, so I can just skip on to the next thing. If it can see it, it's going to be some vertical offset away from that Y line that we're interested in. So it might be up here and the Y might be down here. So there's some vertical distance. So we're going to take that away from our total Manhattan distance that sensor can see. So now we know we come down, we hit a point somewhere along this line, and now there's some space plus or minus from that point that our sensor can see. So that gives us basically a range of values, from a positive and negative range of values around some point X along that line. We can figure out what those are. So we figure out that I'm going to call these a from and a to, and then I stick that into this array of detected points. So now this is for every sensor that can see that line. This is all the possible points along that line, but it's not actually all the possible points. It's just the numbers that represent the start and ends of those ranges. That becomes important as you get into the actual input, because the actual input has numbers in the millions. So if you were to try and actually create these arrays to try and do this, it wouldn't work. So, well, it does work, because I did do an implementation of this where I used hashes to figure out like maps of points, and it did work, but it was very, very slow. Now, you'll see in part 2, my part 2 solution is quite slow, but with how slow that approach was, the part 2 solution would never have completed, because I ended up having to brute force part 2 basically. So the only reason that the part 2 worked in brute force was because my part 1 ended up being very efficient. So anyway, we have our list of ranges. So this is all of the possible points that match along this line. So what we have to do now is we effectively have to decompose this line down into all of those ranges that overlap each other. So if I have two sensors, one here and one here, and they come down and they match to 2 points along that y line. They may overlap or they may not overlap. So if they overlap, basically we've got a range, this range comes up here, this range comes up here, they jump over each other, and now they're overlapping at some point. What we basically have to assume is that for part 1, your ranges they'll all overlap basically. And the reason for that is that you're told that there isn't going to be any gap in that line at all, because you're told that there can't be any beacon there. So effectively what we're just trying to find is the maximum and the minimum parts of that range. So you could do that really simply. There's some extra logic in this loop, which I'll get into in part 2, but really you actually don't need to do that. All you actually need to do is, so what this loop does, I'll explain just briefly, is it basically takes a whole bunch of different ranges and it starts comparing them to each other one by one and starts decompressing them down into one range. And that one range that's left should be the entirety of the range. You don't need to do that for this. What you could do is you have all these ranges. You could just flatten the array of all those, nested array of all those ranges and get the minimum maximum value, and that would be your answer. But that doesn't work for part 2. So I prototyped in part 1 to try and figure out a way to do this. And the way I did it was, it's sort of like a recursive loop. It'll just kind of keep spinning. And what it does is it takes every pair of ranges you have, it tests, are they overlapping in some way or are they fully contained in each other? If they are, then it combines them together to make a new range with like the max and the min value. And then it keeps going and does this over and over again. And it'll keep doing it until it just gets down to either to one range. And that one range is the start and the end point of the entirely complete line in this case. Or in the case for the second part, we'll see in a second exactly how that works. So we'll move on to the second part then. So the second part is going to, they change the problem up a little bit, and what they do is they compress your search space. So they say between the coordinates of 0 and 4 million, or 0 and 20 for the sample, you're told that absolutely the sensor is within that, or the beacon that you want is within that, and you have to try and find its X and Y coordinates. So what you basically, the crux of what we're being asked there is, for the line 0 to 4 million of the Y-axis, do your line checking algorithm. So for each Y, do your line checking algorithm. But instead of just telling me that the width is whatever, I actually want to know what the coordinate is for the X. So I want to know if I'm decomposing my sets of ranges down. For this case, because we know there's going to be a break in the line, my end point when I get to the very bottom is going to be two ranges that don't overlap at all, and they have a value, one value in the middle, and that is going to be the X value that we want. The Y value will be somewhere between 0 and 4 million, and that's where we will be in the loop as we iterate. Yeah, this is getting a bit mental, but let's go into it anyway. So we build up our map the same as before. The only thing that I'm doing differently, and yeah, my ranges are the exact same as before, except I have one slight optimization, is that I'm only interested now between 0 and 4 million. So if any value in the range is outside of those, I just clip them off, which is fine. Then what else do I do that's different? Right, yeah, so now max coord up here I have set is between 20 and 4 million. So this is going to execute at most 4 million times. And for each execution, it's going to do the same thing. It's going to work out our sensor values where the sensors hit that line. Each sensor that hits that line, it's going to do that. Then what it's going to do is it's going to enter into that loop, the same loop that we did before, except there's a couple of extra things inside this loop that become important. So there's an extra condition in here that's added in specifically for the case where you've got any two pairs that don't overlap at all. And the reason for that is because the final two pairs won't overlap, so we want to keep those. In the previous example, if we had a range that didn't overlap, we could just throw them away. We didn't actually need those specific ones. In this case, we actually do need them where they overlap, but there's some weird quirks about going through this, which I'll explain in a second, but effectively we need to preserve those, so that's a logical difference here where they don't overlap. And then you'll notice that I also need a breakout clause here now, right? So previously the way I was breaking out was I was determining that I'd gotten down to a single range of points left. That's not going to be the case now. I'm actually going to end up in an infinite loop, because at some point I will hit an area where I've got two sets of ranges. They don't overlap, so they won't decompose down into one range. And we're told there's only one of those, so we know that is our exit clause, but we have to find that exit clause. So the exit clause I have set up here is this counter where it's figuring out if it's if it's gotten to a size of 2, but it has to get to that size a few times. And that's because I did some ugliness down here where I use a shuffle method to basically figure out my pairs. This is where it gets a bit crazy. So you can end up with a range of pairs that won't compare to each other and they won't work. In the previous example, we were able to throw those away. In this one, we're not going to throw them away. We're going to keep them, but we don't want to keep recomparing them against each other over and over again, because then they'll never decompose. So instead, what we do is we shuffle them around and then we put them back in, and eventually they'll shake out to work. You can end up though in a loop here where you need to hit sort of a stack depth, which I've arbitrarily set at 50, and if you've gotten that far, you know for certain that this is actually a final terminating pair, which has the gaps. I'm not proud of this, but it does work. Anyway, it outputs a value, and it takes about 10 minutes to run. Which was enough that I sat there watching it because I had to print out the numbers on screen, and I saw them ticking closer and closer to 4 million. And I was like, well, if it hits 4 million and it doesn't give me an actual answer, then I'll just try and figure it out again. But it gave me the actual answer after 10 minutes, after it hit some value of 3 million something. So there is definitely a way to optimize this by finding a search space to compress that search space from 0 to 4 million to something smart. I'm sure I couldn't think of it, and because of the crazy day I've had, it just didn't want to play well in my head. This was, I'm not gonna lie, this was a bit crazy. There's my first part, runs pretty quickly, and if it didn't run in anything close to that time, I would not been able to brute force the solution for this, which I did for part 2, but I can't run it and show you because that's going to take 10 minutes to run now. So I'm just going to kill that there. I'm leaving that here for today. I'm exhausted. Let's hope that day 16 is a little bit more straightforward, because this one, this really hurt me today. Anyway, guys, I hope you enjoyed it. I hope you've enjoyed my pain, and I'll see you tomorrow for day 16. Bye bye.